سلام خدمت همه عزیزان. خوشحالم که توی 8مین سری سمینارهای WSS دانشکده مهندسی کامپیوتر تشریف آوردیم و در خدمتتون هستیم. لطفاً اگه در طی ارائه سوالی داشتین توی فرم گوگلی که هم توی چت باکس قرار میگیره و هم پشت صندلی جلویتون قرار داده شده میتونین سوالاتتون رو بپرسین و یک رو مونده به پایان ارائه این فرم بسته میشه و بعد از پایان ارائه این سوال ها مطرح میشن و حالا پاسخ داده میشن، ولی خب به خاطر محدودیت زمانی که داریم ممکنه برخی از سوالات پاسخ داده نشن که پیش از این مورد عذرخواهی میکنیم. و حالا میریم سراغ مهمون عزیزمون که خیلی خوشحالیم که در خدمتشون هستیم. آقای دکتر احسان عادلی، استادیار گروه روانپزشکی و علوم رفتاری دانشگاه استنفورد هستن که در آزمایشگاه علوم اعصاب محاسباتی و بخش‌های PhD و CNS دانشگاه استنفورد کار میکنن و علاقه تحقیقاتیشون شامل بینایی کامپیوتر، هوش محیطی، علوم اعصاب محاسباتی و تحلیل تصاویرپزشکی هست و ایشون یکی از ویراستاران مجله IEEE هستن و اخیراً به عنوان مدیر منطقه چندین کنفرانس برتر از جمله نوریپس، CVPR، AAAI، میکی و ICLR حضور داشتن. خب میتونیم ارائه رو شروع بکنیم. آقای عادلی در خدمت شما هستیم و خیلی خوشحالیم که قبول کردید. متشکرم.
ممنونم. مرسی از اینکه من دعوت کردید. من ارائه رو حالا متاسفانه خوشبختانه به انگلیسی میگم چون خیلی از اصطلاحات یه مقداری سخته برای من بخوام ترجمهش بکنم، اما اگر هر گونه سوالی بود یا حالا هر صحبتی که قبل یا بعدش میکنیم یا حتی اگه سوالی وسطش بود برای کلاریفیکیشن هرچی به فارسی بود مشکلی نداره. خب پس اجازه بدید من شروع کنم. امیدوارم مشکل کانکشن هم وجود نداشته باشه. اگر مشکلی بود هم انشالله به من بگید یا توی چت رو نمیبینم من دارم میبینمش. اگه مشکلی بود توی چت هم به من بگید سعی میکنم رفعش کنم. خب بذارید شروع کنم و خب طبیعتا سویش میکنیم دیگه. Okay, today I'm going to talk to you about dealing with bias in medical studies in the age of large-scale models, a topic that is of great interest and importance, especially these days. Let's start with defining large-scale models. I'm sure you've heard about LLMs. Large language models, or LLMs, are computer programs for natural language processing that use large-scale deep learning and neural networks. They are a recent breakthrough in AI that enable us to build more intelligent systems with a richer understanding of language than ever before. You have for sure heard about ChatGPT, a chatbot developed by OpenAI and launched in last November. It is built on top of OpenAI's GPT-3 family of LLMs and has been fine-tuned using both supervised and reinforcement learning methods. LLMs functionality can be segmented into 5 areas: knowledge answering, translation, text generation, response generation, and classification. And many big players in the industry are developing state-of-the-art models. There are many names here. I'm not going to go into the details. But we know that large-scale models are not limited to language models, are not limited to LLMs. Large models also known as foundation models, or FMs, can solve many other tasks beyond language processing. For instance, you may have heard about DALL-E, which is an image generation framework and clip that connects text and images. These models have also found their ways in processing videos and medical images. Foundation models are large-scale models trained using self-supervision on broad data, or in other words, data that does not require manual annotation or a human intervention. The data could range from text to images, speech, structured and tabular data, or even 3D signals. And therefore, they can be adapted to a wide range of different tasks, from question answering, sentiment analysis, to information extraction, image description, object recognition, and other tasks like instruction following. We released a report in August 2021 titled, as you can see in this slide, on the opportunities and risks of foundation models, which has 26 sections on their capabilities, applications, technology, and society, led by student and faculty leads at Stanford University. One of the main aspects of foundation models that we explored in our report was around their potential harms, which relates to our topic today. We have observed that LLMs and FMs may generate offensive content on different topics. One example you can see here, or they can simply generate untruthful content. See the example here about like Stanford University, its origins generated by GPT-3, which is not correct. Or even they can enable disinformation. It's very funny that some LLMs, this is GPT, they think that climate change is the new communism. This is mainly because they are trained at large scale on broad and unvetted data. Now, suppose we want to use such models in healthcare space and medical applications, which is actually happening right now. They are finding their ways in different applications, in different medical applications. And there are many, already many interesting examples of using LLMs and FMs in healthcare domain. A very recent example is CAD, which describes an interactive computer-aided diagnosis on medical imaging data using LLMs. In this work, Wang et al. Proposed a framework that uses LLMs to enhance the output of multiple CAD networks, computer-aided diagnosis networks, and they use this as their LLM. They use, as you can see here, GPT. The CAD networks, computer-aided diagnosis networks that they used are for diagnosis task, lesion segmentation, and report generation networks by summarizing and reorganizing the information presented in natural language text formats. This is an example of how they generate a report and plainly explain the findings out of medical images, X-rays in this case, this example that you see. It provides a nice interactive question answering platform explaining the images. Another example is the Biomed LM, which formerly was known as PubMed GPT. It was trained exclusively on biomedical abstracts and papers from PubMed. PubMed is a library of publications in medicine, which is managed by National Institutes of Health. So this GPT-style model can achieve strong results on a variety of biomedical NLP tasks. This study concluded that LLMs are remarkably versatile and deliver significant improvements when trained on domain-specific data, while focused models can achieve high quality with relatively few resources. The latest version of GPT, or GPT-4, this is another example, which actually came out, as you can see the date, 6 or 7 days ago, depending on where you are on Earth. Right now, actually, in where I am, it's 15 minutes after midnight. So still, I can say 7 days ago, not 6. Okay. The latest version of GPT, or GPT-4, has been recently tested for medical knowledge, as illustrated in this special report published in one of the most prestigious medical journals, the New England Journal of Medicine. This report was published last week, as I told you. It is showing how GPT-4 can be used for medical note-taking, inference over innate medical knowledge when asked questions like medical test questions even, or even for medical consultation. However, as I explained earlier, and we explained in our report, our published report, biomedical foundation models are not limited to the use of LLMs, although LLMs have been being used in the past couple of months very significantly, but they are not limited to LLMs. They can be based on any data source, not just language, any data source or modality, including text, electronic health records, images, and so on and so forth. And they are not limited to any specific downstream tasks. They could be used for any kind of tasks, including classification or segmentation, and so on. We know that in medicine, bias-driven discriminatory practices and policies not only negatively affect patient care and the medical training environment, but also limit the diversity of the healthcare workforce. We already see several sources of bias in current practices that can simply be injected in data and therefore create biased models when we use them to build large-scale models. For example, a device can be biased if the design disadvantages several groups on the basis of their attributes, such as skin color. As an example, pulse oximeter, as I'm showing in this example, detects changes in the light passed through skin and are less effective in people with dark skins. Computational techniques such as LLMs and FMs that I just talked about are biased in training data sets that are not representative of the population. Interpretation of the results may itself be biased according to demographics groups, for example, when using, for example, correction factors. I don't want to go into the details of the example. This is a spirometer used, but for different ethnicities, it may need different correction factors, which may create bias if it doesn't understand the differences in ethnicity, as you can see in this example. So, In this space, we've done several works on modeling bias and something we call it in medical study, confounding effects. So bias and confounders in medical studies, which I want to talk about today. These are mostly technical works. The methods I present here can be applied to all types of models, including foundation models and large-scale models, to mitigate the confounding effect or the bias in the obtained results. Let me first define confounders. A confounder is a variable that influences both the output or the outcome and the input or the exposure in the study, causing a spurious or distorted association between the input and the output. When building a model to predict the outcome from the inputs, if the confounders are not properly controlled for, we may obtain inconclusive results. For example, when we predict the diagnosis from, say, brain images, age can confound the study because we know that at different ages, human brain looks differently, and hence brain images are largely affected by age. At the same time, we know that the disease diagnosis could be a function of age as well. For example, this diagram shows the distribution of Alzheimer's disease patients in each age bucket, and this one shows distribution of HIV diagnosis as a function of age. So the variable age has a strong effect on both the input and the output of the study. So there are even more examples. Furthermore, for example, if data set itself could be biased by age, having different age distributions in the cohorts or the groups under study. If you have two groups in the study, like a diseased group and a normal control group, and they have different age ranges themselves, this itself creates a very simple bias. If we do not appropriately control for these confounding effects when building machine learning or deep learning models, or even large scale models that are even more blind to the data, we may be learning the effect of age instead of the actual disease effect, because what we are interested in building and learning in this model is the disease effect. But if we don't control the effect of these in this example, age or confounding variable, we may only be learning the effect of that confounding variable. It is not just age. All other demographic variables or even treatment procedures, medication usage, or disease comorbidities can also induce sorts of confounding effects. The literature offers several traditional methods in this space. The first one, and probably the easiest, is data stratification, in which we simply stratify or group the participants in buckets with similar values of the confounding variable. For example, different age ranges, as you can see in this example. And then we build different models for each of the groups. This is an interesting method, but it basically limits the number of samples each model is trained on, which is not of great interest when aiming to train large-scale models. Basically, it's limiting your trained models on a small cohorts or smaller data sets when you group or stratify them. Another method is matching. In this method, for each class of the outcome diagnosis variable, for example, we select a subset of the participants such that the groups are matched with respect to the confounding variable. Although this is a method that helps building less confounded models, it can't guarantee perfect independence from the confounding variable. Plus, it discards some samples that could otherwise be used for model training. One of the most relevant methods is to statistically remove the confounding effect from input variables. To this end, we replace the images with some features such as, like, if it's brain images, it's the volumetric region of interest measurements, some measurements, some features that we extract from the MRI brain image. We then residualize the confounding effects from the features and replace them with new values. To do this, we build a simple linear model between the confounder, the confounding variable, and one specific measurement. So for each measurement, or for each feature and the specific confounding variable, we build this linear model. Then the new feature value will be the previous value minus the amount which is explained by the confounder. So this linear model is showing the amount of the measurement that is explained by the confounder. In this case, these dotted lines will be the new feature values. So this is a widely used method in statistics, and it has been used in many traditional machine learning algorithms too, but it requires pre-computed, handcrafted features because you want to build this linear model on the features. When it comes to end-to-end training, the residualization method does not apply anymore because you don't have any features anymore. You only have the pixel, or in this case, voxel values. And hence controlling for the confounder is not a trivial task. To recap, end-to-end learning involves a subnetwork that extracts features, let's call them F, and then classifies or predicts the output Y. After training this model, we can use different methods for interpreting the learned models. For example, GraphCam and methods that perform layer-wise backpropagation. But the question is, how should we account for the confounders? So this is a typical end-to-end learning framework that is being used even also in larger scale models. So in this space, we have published several works on interpretation of results in presence of confounders, learning features invariant or independent from confounding effects, and finally building models in truly end-to-end fashion, which I'm going to talk about here. Back to the end-to-end learning setting and framework that I just explained. We know that we can interpret the models by using saliency map visualizations, GraphCam methods, and so on that I just explained. To make interpretation of an end-to-end model, which is already trained, this end-to-end model, let's say it's already trained. We want to make interpretation and see, like, what is the effect of that specific confounding variable, like, for example, age. So what we do here is we analyze each of the learned features. We know that end-to-end models, they generate features, extract features first, and then perform classification on top of them. Before classification, we also have this prediction score, which is basically softmaxed to create the binary label diagnosis. So what we do is we perform the exact same traditional linear model that I just explained using the features. The outcome variable and the confounding variable, which is shown by variable z here in this formulation, we basically build the general linear model, or GLM, the same linear model that I just explained that they used to be doing it in statistics, and perform a statistical significance test to see if the each of the features fj is confounded or not. So for each of the single features, we create the same linear model between the confounding variable and this feature. We also have some addition. This is the bias, and this one is we basically use the S variable. When we build this linear model, we want to make sure the features still preserve the information that is predicting y, but we want to remove the effects of z. So basically, this formulation guarantees that. And then after training this, we look at the significance of the values of beta 2, which are the coefficients of the confounder, and then we generate a mask. So after we generate this mask, we plug this back into the model within the, like creating a dummy layer here, and perform a partial backpropagation. And this partial backpropagation generates basically confounder-free saliency maps for each of the inputs. Basically, through this process, we mask any feature that is confounded and only keep those that are unconfounded. And this mask that we generate are thought to be confounder free. We also, so basically we tested this on a number of different applications. One of the applications I want to talk about here is we tested this algorithm for the task of identifying sex differences, gender differences from MRI images of children. We ran this on a data set called ABCD, Adolescent Brain Cognitive Development, which we also actually used this data set to run a challenge in 2019, 2019. The pre-processed data and everything is still available from that challenge that we ran. In this study, we found that pubertal development scale, PDS, was the significant factor. It was significantly different from boys, between boys and girls, because this data set was a data of boys and girls from the ages 9 and 10, and because of this huge difference, significant difference with a very small p-value between boys and girls, this was definitely a confounding factor in the study. Because we were interested in understanding the effect of the variable gender or sex in the brain, we wanted to make sure the differences of boys and girls are being considered, not this specific variable that is not related to, or maybe it's not this interest in this study. So we ran our method on this. We trained a classifier to classify the output of boy or girl from only brain images, and then try to see if we can remove the effects of this PDS scale, PDF variables. So our initial saliency map, heat map, was something like this. And then when we generated the confounder-free maps, removing the effects of the PDS variable with the same method that I just explained, we got the second map, and this third map is basically the difference between the two initial and confounder removed effects. And this is basically showing that the PDS variable was creating an impact more on this region of the brain, the cerebrum regions in the brain, and the rest of the voxels or regions that we saw in the brain are the differences between boys and girls in that age range. We were able to, from those heat maps, explain it even a little bit more. From those heat maps, we could extract the specific regions. Our algorithm found different between boys and girls at ages 9 and 10, which is published in a paper in the Neuroimage journal. Some of these regions had significant differences in their volumes as well when we looked at the specific volumes in the brain. So, because probably the audience is mostly coming from technical computer sciences and engineering backgrounds, I don't want to go into the details of the neuroscientific findings of these results, and I'll stop just here explaining the method. In the second part, now I want to go to the second set of methods that we've published. Now that we have seen how we can interpret a learned model, let's see how we can learn a model, learn features that are independent from, or they are invariant to the specific confounder or bias variable. To this end, we trained an adversarial model that learned to extract features F based on which we predict label Y, while invariant to confounder C via adversarial component, which we called it CP. So again, to reiterate, we extract features that predict Y, but they are invariant to C. So we add an adversarial component. I'm sure that most of the students and audience are familiar with GANs, with generative adversarial networks. This is an application of GANs for training models that have like invariant features invariant with respect to a bias or a confounding variable. We designed a batch level loss function based on correlation coefficient between the actual and the predicted bias variables, or the confounding variables. And the classifier used a regular cross-entropy loss. Therefore, the overall objective of the model will be defined as a mean-max gain between the CP component and C, very similar to GANs, with the trade-off hyperparameter lambda that we use here. Our method guarantees mean statistical independence between the learned features and the the confounders or the bias variables, using our proposed loss function, this Pearson correlation loss function, and a training framework that we called it this vanished correlation scheme. I will leave the details for everybody who's interested to refer to the paper for the theoretical analysis and more details. However, this method was interesting. We ran it on different applications. This one that I just presented. We ran it on different applications. For example, considering race when we want to classify male, female from face images, for example, or many different applications that bias is a big concern. But when it comes to medical applications, we have more challenges, which I'm going to highlight here. In medical studies, we have to we have this additional challenge that to understand this challenge, let me actually give you an example here. Say we have two classes of data, a diseased class and a control class, a normal control class, that you want to classify these two classes of data. So there is already intrinsic correlation between confounder and the disease label Y, or the outcome. I just talked about it before, that these features should be invariant to C, but at the same time we know that the confounder and this Y variable are already correlated. There is a high correlation between those. So basically C is impacting both, influencing F and Y at the same time. We want to remove the effect of C on the features, but what do we do with the indirect effect? So in medical studies, the challenges are more pronounced, and therefore, because of these challenges, it could not be simultaneously true. We cannot simultaneously predict Y from features F while the features are invariant to the confounder C. So to solve this problem, we need to enforce the invariance condition only based on one of the cohorts or classes. As you can see here in the previous one, if you say this is the effect that you want to remove, now we know that like there is that effect between like on the class itself. So we basically put a condition on the effect that we are learning, and we only look at one of the cohorts. In this example, we select control, and in many of the studies, clinical studies, is basically the control that is selected for removing the effects. As a result, we designed a switch row which makes the adversarial head CP only backpropagate the loss for the control group. This means that it is Y conditioned. Doing so, we showed in the paper that F will become mean independent from the confounder C. This is a paper we published in Nature Communications in 2020. We solved this problem using the same min-max adversarial training framework that I told you, and only enforced rho in the second term and the adversarial component. So it's a Y conditioned adversarial learning. We tested this model on our lab data for HIV classification from brain images again, which has age as a significant confounder here. We showed improved accuracy compared to when the model was not controlling for confounding factor, meaning that this independent feature learning not only removed the bias from the confounder age, but it was also able to regularize the model to generate better model to unseen testing data. This was further verified by looking at each matched age bucket. Again, significant improvements when we remove the effects in this matched age bucket, and as well as when we specifically evaluate on young and old sub cohorts. The visualizations of the learned features by the models, like in the middle, as you see, shows that our model's feature space is not biased by age, while a regular confidence feature space clearly shows a pattern with respect to age. You can see this pattern here. The plot on the left shows our model was able to generate correct predictions for both young and old cohorts, while the ConvMed model, the baseline model, was basically biased by age. And interestingly, when we do this visualization, you see on the right, we also show that the saliency maps, which again show successful removal of the regions that are called, you see these regions that are removed by our method. These regions are called ventricles. Ventricles are very much known that they basically enlarge when people age. So by aging, there is the direct effect of those regions, the direct effect of age in those regions, and our model, without knowing this knowledge, only based on data, was able to remove the interpretations from those regions, which actually match the neuroscience literature as well. So this was some work and results for showing that how we can learn independent features. I want to explain and talk about some methods that we proposed more recently for end-to-end learning for controlling the confounding effects. For the end-to-end training of the model, you know that we used to be using like batch normalization. Batch normalization and its variants have been extremely successful in improving the training of machine learning models by standardizing features within a batch. However, they, okay, I still need to go back, okay. However, they do not correct the distribution of the features with respect to external variables. In this paper, we refer to them as metadata, but you can consider them still like as confounders. This paper is solving the problem in a more general way. So again, just to recap, batch normalization fixes the feature distributions only based on that specific feature, but it doesn't care about like the confounding variables and extra variables that could be influential in the feature, like on the feature. So in this paper, we wanted to solve that problem. But on the other hand, as a recap, as I discussed before, prior methods which remove the impact of protected variables included using this regression analysis, the GLM model, which is a common technique which builds a linear model between features and metadata, and then takes the residual between features and this linear model as the new input. However, this technique only works for high-level hand-computed features, as I explained before, because we want to build this GLM model on the features, not on the pixel level or voxel level data. And for batch normalization, I explained that they can't account for multiple or biased distributions. And these prior works are not that useful when there is bias. This is why in this recent work, we proposed a simple layer that works end-to-end on pixel or voxel level data and corrects the distribution shift from metadata. MDN, or metadata normalization, places the regression analysis technique within the network using the key idea that intermediate features of the network may be high-level features. So in a network, at an input layer L with features F, the features will be the input to the MDN operation that we want to define. It is projected onto the metadata space in a very simple and similar to I explained earlier in the linear fashion, and then the output of the residualization, it becomes the features for the next layer. So in this way, what we do is building, like bringing in that statistical model into the end-to-end training framework. We tested the algorithm on a data set from 3 different sites, from the 3 different sites that I'm explaining here. It's an ADNI, Alzheimer's disease neurodegenerative initiative. Our lab data and also some data that we have acquired from UCSF, a lab in University of California, San Francisco. The goal for this data is to understand the impact of the HIV, the virus and the disease, and mild cognitive impairment, brain cognitive impairment, and their like compounding effect, which is called hand HIV-assisted neurodegeneration. So we wanted to understand these effects. We wanted to build a model that removes the effects of site, because there are site differences. First, because each of these sites have limited data, we had to gather like more data from different sites, different locations. But when you're getting data from different locations, you're actually creating a bias. We wanted to remove that effect of the bias. So what we did was we tested the algorithm on this. The site variables was considered as a confounder that we wanted to control for. Basically, this procedure aims to remove the effect of site differences, and in other words, harmonize the data. Our results show that MDN operation is able to not only generate better accuracy for classification, this is a multi-class classification task, but this is a significant classification result, with more reliable standard deviation in classification, and finally the minimum correlation between features and the site. You see the correlation for other methods is actually very high. D-core is a distance correlation. It's a correlation metric that we use as a metric for showing if we were able to remove the bias or not. We also looked at the feature spaces. This was also shown in the visualization of the feature embedding space, where we see that the method with MDN does not show any pattern of bias with respect to the 3 sites. When we are not using MDN, you see that there are clusters with respect to site, while we want to learn features that are not biased by site. So this one is more agnostic or invariant to the variable site. So to continue, we did this. We did see the solution to MDN, which was basically what it does is using the just to summarize, using the metadata variable and input features from all of the samples in the batch. So this is a batch level operation. We use the data from the batch to compute beta using closed form solution of this least squares problem. The metadata variables and beta are then used to calculate the residual R given to the next layer of the network. The network is then trained using the overall prediction loss as seen here. So this whole process is a batch level operation. So this is a closed form operation solution. We need all of the data in the batch to be able to build this closed form solution and linear model, and then generate the output R. So this makes it confined to batch size, and dependent on batch statistics, a characteristic that makes MDN operations suboptimal for small batch sizes and mainly unstable for many novel architectures. Like, for example, these batch level operations are not, they cannot be used in more novel transformer architectures, which they parallelize the training. So to overcome these limitations, what we did was we proposed a penalty approach to MDN, which we called it PMDN, which turns the beta coefficients to network trainable parameters. They can be optimized by regularizing the loss function. So instead of calculating betas in a closed form solution, we just turn the betas as parameters, trainable parameters, and use them for regularization of the original loss function of the network. So we tested the algorithm on the same data set as I showed before. And this time we can see that for all of the batch sizes, even for small batch sizes, we get consistently very high accuracies, while MDN itself is showing like decreased performance in small batch sizes, although large batch sizes is not that bad. And then in terms of accuracy. And in terms of correlation with different variables that we included in the study, we are also minimizing the correlation with PMDN better than others. This adversarial paper 2 is our own previous work that was published in Nature Communications that I presented a little bit earlier. In some cases, it was more stable in removing the correlations for some of the specific variables. So these are our results. Here I want to conclude the three categories of methods that I presented here. And as a takeaway message, we learned that accounting for confounding variables is essential to drive meaningful and reliable findings. Especially this was very important for us in neuroscience studies, because in neuroscience, we don't very much care about the prediction or the classification task itself, but we care more about what we learn from that classifier, how the brain is performing, or what is the differences in the brain that creates this specific disease, for example. So at the end, I'd like to thank all my amazing collaborators, all of them at Stanford, and the students who I presented their works here. And thank you, and I want to also thank these institutes for supporting my research. I'll stop here. If there is any question, I would be happy to answer. I did try to keep that talk to less than 1 hour, not to bore everybody, and leave the time for question answers.
Thank you for your great presentation. It was really fascinating. Thank you. There are some questions that people asked. Let me.
اگه همه آدینس ها فارسی تو ایرانن میتونید فارسی هم صحبت کنن دیگه. من حالا وسطش کلمه رو انگلیسی میگم، ولی خب دیگه
چشم. یک لحظه. خب سوال اول در مورد اسلاید شماره 7 هست که آیا در تصویربرداری پزشکی تفاوتی بین زنان و مردان وجود داره؟ تعداد نمونه‌های داده‌های آموزش زنان و مردان تاثیرگذار هست؟ بین نژادهای مختلف چطور؟
اسلاید 7 فکر می‌کنم دیگه همین باشه. در مجموع سوال خوبیه، چون خیلی از من نشون دادم این مقداری که کلاً تفاوت بین مرد و زن توی خیلی از استادی های نیوروساینس نشون داده شده که یه سری تفاوت های خب بالاخره وجود داره بین مرد و زن و به همین دلیل هم سعی میکنن که همیشه تعداد نمونه هایی که توی دیتا ست ها میگیرن بالانس باشه. ولی به شکل بعضی موقع حالا جالبی تو بعضی استادی‌ها تعداد زن‌ها کمتره، تو بعضی استادی‌ها هم تعداد مردها خب کمتره، بسته به مثلا نوع بیماری خاصی که دارن بررسی میکنن. خیلی فاکتورها هست توش، مثلا بعضا نشون داده شده مثلا تو بعضی از ریژن‌ها تو خانم‌ها خیلی علاقه ندارن که توی استادی‌ها مثلا شرکت کنن، بیشتر آقایون مثلا میرن شرکت میکنن. خب پس این مشکل هست توی کلا توی استادی‌ها، توی همه دیتا ستایی که تقریبا ما کار میکنیم. ریس و خب اتنیسیتی های مختلف خیلی خیلی بیشتر، چون بسته به این که استادی کجا داره اتفاق میفته، عملا همون پاپولیشنی که دموگرافیک اینفورمیشنی که همون پاپولیشن دارن معمولا رفلکت میشه توی دیتا، که مثلا اینجا که ما هستیم دیتایی که لب خودمون میگیریم یا مثلا همین UCSF که گفتم توی این سان فرانسیسکو بی ایریا پاپولیشن مثلا وایت و خیلی زیاده، خیلی پاپولیشن educated خیلی بالاست که خب دیتاهایی که میگیری باز نوعتا میشه از لحاظ سوسیو اکونومیک استاتس و اینها متفاوته. بایاس همیشه توی دیتاها همیشه هست. کاری که دارن میکنن سعی میکنن که تا جایی که میشه بیشتر و بیشتر دیتا ستا رو بالانس ایجاد کنن با توجه این وریبل هایی که میشناسیم. ولی در این حال این متدایی که من سعی کردم نشون بدم اینه که اگر دیتامون هم تا حدی یه مقداری بایاس باشه، با این متدا میتونیم یه مقداری این افکت رو ریموف کنیم موقعی که توی ترینینگ، در زمان ترینینگ ما.
متشکرم. سوال بعدی این هستش که با توجه به این که توی ایران سهم زیادی از دادای پزشکی رو کلا ندارن، بحث حذف سوگیری ها چقدر معنادار هست؟
نمی‌کنم متوجه نشدم چی رو ندارن گفتین؟
تعداد داده های پزشکی که حالا دادای درمانی که وجود داره برای آموزش مدل ها زیاد نیست. پرسن که چقدر معنادار هست این کار.
خب هر مدلی که میخوایم تولید کنیم طبعاً خب دیتا توش بحث اولو داره دیگه. یه سری اصلا همین کار آخر که من نشون دادم این بود که این مدلایی که ما ترین کردیم، چون دیتاهایی که از چند تا لب مختلف آوردیم، این فقط مشکل ایران نیستش، مشکل دیتای پزشکی همیشه همینجوریه که به خاطر مسائل پرایوسی تو آمریکا یه مقدار حتی بعضا سخت‌تر هم هست، خیلی سخت‌تره. به خاطر مسائل پرایوسی دیتاها اکثرشون پابلیکلی اویلیبل نیستن. بنابراین معمولا اینستیتوت‌های لبا با هم دیگه باید کار کنن، یه سری اگریمنت‌های بین هم امضا می‌کنیم که این دیتا ها رو مثلا پرایوت نگه داریم، شیر نکنیم و غیره. به خاطر یه سری هم توی آمریکا هم توی اروپا، توی آمریکا به خاطر هیپا، توی اروپا به خاطر GDPR خیلی این بحثا حساسه. بنابراین این فقط مختص یه جای خاص نیستش. با همین کاری که کردیم مثلا دیتاهای مالتیپل سایتس رو کنار هم میذاریم و با استفاده از این روش سعی میکنیم که این افکت هایی که از مثلا سایت های مختلف از جای مختلف ممکنه ایجاد شده باشه رو از بین میبریم. یه چیز دیگه این که تو بعضی از این استادیا که میتونن دیتا ها رو دی آیدنتیفای بکنن، پابلیکلی هم دیتا رو معمولا میشه بهشون دسترسی پیدا کرد. مثلا یکی از دیتا سیتی که من نشون دادم همین ABCD یه دیتا سیتیه که الان پابلیکه، البته ممکنه که توی ایران هم چنین مشکل داشته باشه برای گرفتنش، چون از NIH آمریکا باید اجازه بگیرید برای دانلودش، ولی نشنال دیتا آرکایو آمریکا، ولی دیتا پابلیکه. یا مثلا استادی ادنی اون آلزایمر دیزیز که در موردش صحبت کردم، اون پابلیک UK بایو بانک، دیتا ست خیلی بزرگ، خیلی کامپریهنسیو، خیلی خوب، خیلی کاملا پابلیکه. اون فکر کنم حتی گرفتنش اونقدر هم نباید سخت باشه. جدا از اون نیست، استادی هستش که توی استرالیا است و در مورد این استادی ها چی صحبت میکنم، من فقط برین ایمیجینگ. و یه استادی خیلی بزرگی هستش که دیتاش توی چین جمع شده که معمولا چک کردنشون اونقدر هم سخت نیست برای کسی که تولیدش کردن.
متشکرم. سوال بعدی از اسلاید شماره 26 هست که آیا نیازی نیستش که ابعاد فیچر از همدیگه دیسنتنگلد باشن؟ این مشکل توی این ماسکینگ ایجاد نمی‌کنه؟
تا حدودی چرا؟ اون کاملا حرف درستیه، سوال درستیه. اگر بخوایم کاملا این فیچر رو مطمئن باشیم که هیچ افکتی از بین نمیمونه، چرا این فیچرها باید دیسنتنگل باشن؟ اما فرض ما توی این کار این بود که فرض کنیم که یه مدل رو قبلا ترین کردیم روی دیتا خیلی زیاد و هیچ راه دیگه هم نداشتیم که برای اینکه اون دیتای بزرگ بوده، بعد مثلا حتی بعضا اون وریبل های بایاس اینا رو مثلا روشون نداشتیم که بخوام موقع ترین کردن اون اطلاعات رو در نظر گرفته باشیم، مثلا متدای بعدی که توضیح دادم. اگر مدل آردی ترین شده باشه، با این روش میتونیم اونهایی که این دونه فیچرهایی که سیگنیفیکنتلی افکت دارن و حداقل افکتشون رو حذف کنیم موقعی که میخوایم دیتا رو اینترپرت کنیم. ولی سوالی که میپرسید right to the point و کاملا بجاست و طبیعتاً اون نیاز داره که ترینینگ رو تغییر بدیم. نمیشه این مدلی که قبلا ترین شده رو فیچرش دیسنتنگل کنیم، بخاطر اینکه ترینینگ لازم داره که شما اون وریبل ها رو جدا داشته باشی، بتونی یه دیسنتنگلمنت بین فیچرهایی که توی لیتن اسپیس هستش ایجاد بکنی.
متشکرم. سوال بعدی از اسلاید 47 هست که پرسیدن که میشه توضیح بیشتر در مورد متا دیتا اسپیس بدید و پروجکشن روش که چه معنی داره
دقیقاً. این دقیقاً همون نموداری هستش که مثلا من توی اسلاید میتونم اینجا رو بگم، مثلا اینجا هم نشون دادم. متا دیتا همون وریبلیه که شما مثلا بایاس دارید روش یا مثلا کانفاندینگ افکت داره ایجاد میکنه. هر فیچری که توی مدلتون دارید رو شما وقتی میخواید اون افکت رو ریموو کنید، مثلا این فیچر اگه یک سمپل خاصتون این ولیو فیچر رو داره، این لینیر فانکشنی که اینجا تولید کردیم میاد اکسپلین میکنه میزانی از فیچر رو که با متد دیتا اکسپلین شده. یعنی برای این سمپل این بخش دیتا، فکر کنم موسمانه که اصلا من میبینید، این بخش از دیتا اکسپلین شده با اون افکت متد دیتا و اون بقیهش، اون ریزیجوالش هستش که برای ما مهمه که چقدرش میمونه که به خاطر تاثیر متد دیتا نیستش. حالا کاری که ما اینجا انجام دادیم همین متد دیتا اسپیسی که در موردش صحبت کردیم، این همونه، ولی توی های لیول های دیمنشنال اسپیس. این متد دیتا اسپیس برای اینکه ما متد دیتامون فقط یکی یا دو تا وریبل نیست دیگه، یه فضای ممکنه تعداد خیلی زیادی داشته باشیم که یه فضای های دیمنشنال ایجاد میکنه. همون لینیر مدل رو توی فضای های دیمنشنال داریم تولید میکنیم، یعنی شهودی عملا همونی که قبلا توضیح دادم.
متشکرم. یه سوال دیگه هم این هستش که این انگلیسی پرسیدن. Doesn't autoencoders work better for feature extracting because of embedding to a low dimensional space instead of GANs?
سوال جالبیه. ببینید همه حالا میدونم باید سوال انگلیسی جواب بدم یا نه، ولی در مورد گن ها بذار من برم روی همون اسلایدش. این حالا این مدلی بود که مدلی بود که در موردش صحبت کردیم. ببینید توی آتو انکودر هم شما همیشه یه فیچر اسپیس دارید، یه فیچر اکسترکتور دارید، انکودر دارید، یه دیکودر دارید دیگه. حالا اینجا هدف از فیچر اکسترکشن اینجا برای هدف برای کلاسیفیکیشن، میخوایم یه چیزی رو کلاسیفای کنیم، یه وای داریم. آتو انکودر وقتی شما میخواید خود تصویر رو بازسازی کنید، یعنی عملاً یه فیچر جنرالی تولید میکنید که اون فیچر جنرال تصویر رو بازسازی میکنه، حالا میشه داون استریم برای کاربردها دیگه هم استفاده کرد ازش. عملاً انکودر این فیچر اکسترکشنی که من اینجا گذاشتم میشه همون انکودر یه آتو انکودر، ولی خروجی که داریم برای ما مهمه دیگه اون ریکانستراکشن نیست. اینجا من که ما یه تسک دیگه داریم، میخوایم کلاسیفای کنیم. این فیچرها رو میخوایم فیچرهایی باشن که دیتا رو کلاسیفای میکنه، نه فیچر جنرالی که میتونه مثلا میتونه ریکانستراکت کنه. ولی در نهایت خیلی هم فرقی نداره، چون که این انکودری که شما توی انکودر رو صحبت میکنید همین فیچر اکسترکتور است. و اگر بخواید برای اتو انکودر هم حتی بایاس رو ریموو کنید، چون نیاز به این ادورسریال کامپوننت دارید اصلا، یعنی اصلا کلا یه بحثش کاملا جداست. هم این ادورسریال کامپوننت بالاخره اگر از این روش بخواید استفاده کنید باید به همون هم اضافه بشه.
متشکرم. یه دونه سوال دیگه مونده که اینم یه مختصر جواب بده. متشکرم میشم. متدهای کلاسیک برای حذف کانفاوندر مثل سامپل ریویتینگ آیا استفاده میشن تو کارهای مدیکال ایمیج و اگه استفاده نمیشن نقاط ضعفشون چی هست؟
چرا؟ اونم یکی از روش هاست. حالا من در مورد روش‌هایی صحبت کردم، بیشتر روش‌هایی که در موردشون صحبت کردم این روش‌های استراتیفیکیشن بود. مثلا استراتیفیکیشن یکیش بود مچینگ، حتی یکی دیگه شما با مچینگ هم یه جورایی انگار داریم ویت چیز میدیم دیگه، ویت 0 و 1 میدیم. حالا اون ویتینگی شما داریم دیگه دیدین که من به جای که دیتا رو ریموو کنم اون یکی که سامپل مثلا تعداد کمتری داره ویت بالاتری بهش بدم. از لحاظ استفاده میشه، ولی از لحاظ چیزی، از لحاظ پرفورمنسی خیلی قابل مقایسه است با این روش‌های مثلا دیتا مچینگ و استراتیفیکیشن. ولی درسته یکی از روش‌هاش هم اینه که عملاً یا لاس فانکشن میتونه ویت کنید بر اساس اون دیستریبیوشن کانفورمینگ وریبل، یا اینکه اوور سامپلینگ آندر سامپلینگ انجام بدید توی دیتا ورودی.
خیلی متشکرم. سوالات تموم شد. خیلی ممنون از شما که وقت گذاشتین و دانشتون رو در اختیار ما قرار دادین و لطف کردین که
ممنونم. ممنون. امیدوارم که روز خوبی داشته باشید و ساعتی تقریبا 1:01 شب از کالیفرنیا. ممنون. روز خوبی داشته باشید.
متشکرم.